So what we're doing here is looking at a little bit of the chemistry that goes on in the body. And, we talked a little bit about the chemical level when we talked about the structural levels organization. And that was about building molecules, which we're not really going to get too much into as far as this chemical structure. We're really more interested in terms of biochemistry stuff, right? So for this DNA molecule here, we're not so interested in how these stick together, but maybe how they make this shape, right? How this double helix is formed. So, this whole biochemistry aspect, right? This whole physiological, cellular physiology stuff that's going on right here, like this reaction where you're turning two molecules into another, is kind of what I'm talking about here with this basic chemistry stuff. So we're going to want to be familiar with what like H plus means and what these arrows mean and stuff like that. All right. And then the big thing, the really important thing that'll be with you for the entire course is, the importance, the centrality of water in this course. And, the fact that the way water molecules interact with each other and other molecules or don't interact with them is a really important key component of the course, right? So you want to understand this whole aspect of it, right? Number one, things dissolve in water, right? Water is like the background of everything, where you're going to have solutes and different ions floating around in here that are going to be very important, right? And they'll also form the basis of a lot of the interactions between molecules and water, right? That are going to give a lot of importance to the overall structure of things like your phospholipid bilayer and stuff like that, right? This all has to do with interactions with water. And then the other big part about cellular physiology is membrane transport, right? What gets through the membrane, what's going to have to be transported through, right? And even when it is transported through, what do these channels look like that allow this, right? It'll all have to do with water and hydrophobicity, right? And hydrophilic molecules, right? Plus, there's all these little pluses and minuses out here. What do they mean? And how does the cell maintain them, right? So when we're thinking about chemistry, right, we're going way back to the atomic structure of the atoms, right? We'll deal with only a small amount of atoms here. But, basically you have the protons and neutrons, and then you have this electron shell around them, right? And the important part about chemistry is all about this outer shell right here. That's key to all its behavior, right? And so when you do chemistry, if you're trying to memorize it, you're trying, okay, nitrogen has 7, how many electrons does it have? You're trying to do all this stuff. That's not really the way to think about it in my mind. Right? So you have this periodic table, and this gives you all the information you want to know about how atoms are going to interact with each other, right? They have all the names here, the atomic mass, their names, but really it's simpler to not look at those names for a second. Right? You just want to look at these diagrams right here, this sort of planetary model where the electrons are circling around the center. And the key to all this, at how they interact, is looking at this side of the table, right over here. Right? These guys over here are referred to as the noble gases, right? Helium, argon, what's the other one? Whatever these are, doesn't matter. They're all noble. They're considered inert, right? They don't really do anything. They're just floating around because they're complete. They want for nothing. They have no hunger for anything. They're just floating around. They don't interact with these guys. They don't interact with each other. They're just floating around totally at peace, right? So all these guys are called the noble gases, and they're noble. We just have to accept that for some reason, atoms like a complete, and by complete, I mean 8, or 2 in this case, but all the other ones need 8 outer electrons in their outer shell right there. And if they have those 8 electrons, they're happy and they don't need to do anything else, right? So those are the noble gases, right? And we don't deal with them at all because they're inert. Right? So at the other people, all these guys right over here want to be like these noble gases, right? They're lacking in something. They're not complete. They have different numbers of valence electrons, right? They don't have a complete, they don't have 8 shells. They have 7, 6, 5, 4. But they want to be like these guys because these guys are just totally chill, right? These guys are hungry for that. So when you look at a picture like this, a diagram, right, you're going to look at this guy right here, and you're going to ask yourself, what does this atom right here need to do, right, to get to be like this guy right here, right? And in this case, what does he need to do? He just needs one more little electron right there, and then he'd be happy, right? Or she, actually. Right, so that's what they'd have to do. Just get one of those, and then they think they're happy, right? So what about this one right here? What does it have to do? Well, you just count the electrons. Is it 8? 1, 2, 3, 4, 5, 6. No, it's lacking 2. So what does that mean? If it had 2, it would be happy, right? It'd be all good. It just needs 2 electrons, and then it thinks it'll be happy. Will it? What about this one over here? This only has 1. That's 7 less, right? And so it has 2 options. Maybe it could get 1, 2, 3, 4, 5, 6, 7. But that's a tall order. It can't do that, right? So what it's going to do instead is, instead of looking at this guy, he's just going to look at this guy, right? And then cross off this one. And then he thinks he'll be happy, right? He's just going to look at the next one because this guy's happy and he has no chance of being this guy. So we'll just get rid of one of those electrons right there. How about this one right here? He's basically in the same boat as this guy right here. He can't be this guy right over here. So instead, he's going to look at this one and drop an electron, right? And then, at least by valence electron wise, he's going to be looking externally like this one over here, and he'll be happy for whatever reason. We don't know why 8 is a magic number. It just is, right? You just have to, it's one of those things you have to accept, right? So, and then the same would be true for this one down here, except it would have another valence under there, but the outer shell would just be such that it was 1 and it needs to drop 1 to look like this guy, and so on, so on. This one over here, same kind of thing, except he'll have to drop 2 of these, to look like this one, right? So that's the difference between these two. And then this one will also have to drop 2 to look like this guy over here. All right. So then when you start moving over here, you get to about the middle. And you think, well, this guy, he could either drop 4 and look like this guy, or gain 4 and look like this guy. That's kind of a hard choice. So he's in a little bit of a different boat than these ones over here, right? Because these guys over here are very close to this, and they have an idea of what they want to do. These guys have an idea, but these guys in the middle, they act a little bit differently, right? So let's look at 2 of the ones over here that have a very obvious choice, right? Chlorine over here, which could just get one of these and look like that, and then sodium, right? All it has to do is drop 1, and it looks like that. And the question is, will they be happy at that point to do that? So here's the other key point. You have 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6 electrons. If you counted the number of protons, and again, we don't have to worry about neutrons in this case, we're just thinking about protons, this core on the inside, and these electrons, right? The protons will equal the number of electrons in an atom. All right. So that is what the inner core means, right? So when this sodium atom, right here, with the 1 electron, what is he thinking right now? He's thinking of that neon atom, right? All he has to do is do that. Then he just drops this electron, and we call that donated, right? So he drops that, and all of a sudden he looks kind of like that, but then there's something else here, right? There's this positive charge because he's got 11 protons, whereas neon only has 10, right? So this is balanced, this is not. So all that work, and he finds out he's still not happy. He's still got some kind of charge to him, right? So he's not an atom anymore. He is an ion because he's lost that, and now he's gained a positive charge right here, right? So this is an ion, and in particular, because it's got a positive charge, it's called a cation. A cation. That's just the name of it. With me so far? So that's a cation. And then, so, you know, how you'd see this in your notations, right? That would be sodium, a little plus sign. There's also a major one, potassium. There's also, well, let's just say calcium is a big one in this course, except that it has lost 2 electrons. So it's got a 2 plus right there, right? So these are some of your major cations that we'll run into in this course. And the other big one, of course, is hydrogen, right? Because that's going to lose 1 and just be basically a floating proton. And so these are all cations. All right, so there's the sodium atom and ion, and here's that chlorine. Remember, all it's got to do, right? Because what is it trying to do? It's trying to look like that argon right there. It's thinking of that nice complete shell. All it needs is an electron. So what does it do? It's going to find some somewhere, right? And then now it'll have a complete outer shell, right? But it finds itself in the same position because it's got 17 versus the 18 protons, right? So it's got a negative charge because an atom is so-called negative, whereas the protons are positive, right? So that is a what? An anion, right? They're both ions. One's a cation, one's an anion, right? And together, well, let me just actually say for those anions that we're going to run into, right, this is chlorine. You'll see a negative charge. And really the other one, it doesn't have to be just an ion with these charges right here. The other anion we're going to see a lot of is the HCO3, the bicarb ion, right? These are some of the major anions that we're going to see floating around in there. They have 1 extra negative electron there. But together, now that they found themselves not quite as happy as they want, they're going to get together, right? Because one's got a positive charge, one's there. And then together, they can kind of bond together and be together like that in what's called an ionic, because they're ions, an ionic bond, right? And then this gives us sodium chloride, which is normal table salt, right? When it's in non-aqueous solution, right? It's a nice salt. So, you know, that is your chlorine, sodium, magnesium. You'll also have the next one down here. You'd also have potassium, right? And calcium down over here on the next row right there. That'll be big ones, right? For these ions that we're going to run into. And there's also, of course, hydrogen ions, right? That'll be maybe the most major one, right? Going through this will come up over and over as far as ions go. So that leaves us with these ones over here to think about, because these will be the other major organic sort of related molecules, right? So for these, and hydrogen is going to be included in these because they're act a little bit different from these ones that easily form ions, right? They have a different method of filling their valence. So those guys, instead of forming an ionic bond, losing or gaining an electron, right, they are going to instead share one of those electrons, right? So for each, from the perspective of each atom, he looks over and he's got 2 electrons, right? So that's a little bit different from those ionic compounds, right? These are called covalent bonds, right? Because they're sharing equally between the atoms, right? The oxygen molecules look over, and if you count from this perspective, he counts 1, 2, 3, 4, 5, 6, 7, 8. And he does the same thing, right? Sorry, I keep calling him he's. She, how about the nitrogen one? You can count 1, 2, 3, 4, 5, 6. So when they work together, then they will all be having their octet of electrons. So this could be between 2 molecules right here, right? And in fact, hydrogen and oxygen and nitrogen, they don't exist like this. You're only going to find them in this conformation, right? They'll never be single atoms right there because they'll immediately join up with each other or something else, right? So for instance, these hydrogen ions are going to have 4 of them because carbon, remember, has 4 of them. So he can bond with 4. She can bond with 4 hydrogen atoms, right? And they're all equally shared, right, between the two. So that is that covalent bonding, right? And as far as carbon goes, as we'll see, carbon is the most versatile one. That's, you know, the basis of organic chemistry, where a carbon can form, say, 4 hydrogens or 3 hydrogens and another carbon, or 2 carbons and 2 hydrogens, and so on, right? Any sort of number of bonds it could form for carbon. So those are those covalent bonds, and they're all shared equally. The atoms are shared equally around here. As far as that kind of bonding goes, right, you have those 2 types of basic bonding, right? You know, with these atoms with incomplete valence shells can either share them, right? Share them, or they can be stripped or transfer them completely, right? So the sharing part is your covalent bonds, a pair of electrons shared equally by 2 atoms, or the ionic bonds, where the one is completely transferred. And so all you got to know about them is basically their strength. You can start to recognize which molecules form which just by habit, right? But between these 2 bonds, covalent, for whatever reason, is much stronger. That is, it's much harder to break these bonds than it is this bond, as we'll see, right? So as far as the strength of these 2 types of bond, the covalent one, much stronger. So those are those covalent bonds. And then there's another one here, quite famous, this water molecule. When one oxygen gets in contact with 2 hydrogens, right, and they form the water molecule, right? But there's something a little different about this one versus these right here. And if you look closely at the atoms right here, you'll see these little Greek letters, right? And if you compare, for instance, these right here, the carbon molecule, he's all chill, and these hydrogens are sharing with them. They're all at peace with each other. But oxygen is very greedy for electrons, big, strong electronegativity, such that it's grabbing, it's pulling these electrons toward it. And so when it does that, the hydrogen ions, which are weak, and they say, okay, go ahead, right? They develop a little bit of a charge around them, a positive charge, because their electrons are closer to the oxygen molecule. Okay, so that means the oxygen molecule is developing a little bit of a negative charge on this side, right? And you're going to get this, what's called polarity of charge in these polar covalent bonds. So this is a big key concept, right? Polar covalent bonds, right? This will be really the starting point of the important part of, you know, biochemistry and basically the action of water in our physiology course here, right? So hydrogen bonds is that other type of bonds, and they relate to these polar bonds right here, right? So when these get together, right, you have this negative part of the molecule and a kind of a positive part of the molecule, right? So there's a difference in electronegativity within the molecule. And because of that, this water molecule, which has a positive, negative part over here, is going to be attracted to the positive part of this water molecule, and so on and so on. That is your hydrogen bond right there. Right? So it's not as strong as ionic or covalent, but it's very frequent, right? All around here, it's very easily made, right? And it's very fluid right over here. And it's not just water molecules. Anyone like nitrogen and oxygen are the big ones we're going to see. They're going to form these hydrogen bonds, right? A slightly positive part of one molecule is going to be attracted to the slightly negative part of another molecule. The bond is easily broken, right? But it's enough to kind of keep things cohesive and together. So those are these hydrogen bonds, right? And all these molecules, you'll see oxygen, these OH groups, these hydroxyl groups are all going to have this polarity where they're going to be attracted to each other, and water, right? Nitrogen and oxygen are the big ones, these polar bonds. And so for any of these side groups that we'll be looking at eventually, right? If they have these polar bonds right here, they're going to act differently in water versus these non-polar bonds right here, these ones that are non-polar, they're going to act very differently in water. So the whole point of all this, right, when we get here, water is such a big part of what we talk about here. This is a poem from, I don't know, before they knew what water is, right? Water is H2O, hydrogen, 2 parts, oxygen 1. There's a third thing that makes it water, and nobody knows what it is. Well, that thing is hydrogen bonds, right? What this poem was getting at was the sort of emergent property that comes, right? When you put a bunch of these together, it gives water most of its kind of properties that make it the most important non-organic molecule, right? That's key to life, right? Life couldn't exist without water as we know it.